All right, let's dive into something pretty cool today. This idea of making machine learning more interactive, more transparent.
Yeah, I mean, think about it. You're not just getting a prediction from your model.
Right.
You can actually understand, like, how it got there, maybe even spot some biases,
Oh, sure.
and then even better, you can actually guide the model's learning.
Wow. Okay, so that's what we're talking about today, this combination of explainable AI.
Yeah, XAI, XAI, right, with IML.
Exactly, interactive machine learning, and the paper that we're looking at today, it really lays this all out. 2207.14526, Leveraging Explanations in Interactive Machine Learning. An overview.
And it really is a great overview.
It is.
So our mission, if you will, is to really pull out the key takeaways, especially this idea of how different kinds of explanations can actually be used to debug, to edit, and even to teach a model basically from scratch.
Right, and especially in those situations where, you can't just throw more data at the problem.
Right.
There's got to be a better way. More data isn't always the answer.
Exactly.
So maybe before we jump into all the details of the how,
Sure.
can we take a step back and just talk about, like, why is interaction even so important
Oh, yeah, that's a great question.
in machine learning?
So, a lot of traditional machine learning, it kind of operates like this black box.
Yeah.
Right? It gives you an answer, but you don't really know why or how it got there.
Yeah, you just have to trust it.
Right, exactly. And IML is really trying to change that.
So IML is more about giving the user control.
Giving the user more control,
Okay.
more understanding, more of an active role in the whole process.
Oh, so it's not just about having a model that you can interpret.
Right.
It's about this real-time feedback, like a conversation.
Yeah, it's like a back and forth, like you're having a dialogue with the model.
Okay, and that's where these explanations really...
That's where explanations are super important.
Yeah, that's how we build trust.
That's how you build trust, and that's how you get transparency, right?
Yeah.
If you don't know why a model is making a certain decision, it's kind of hard to trust it.
Right, especially if it's something important.
Especially in high-stakes situations, absolutely.
Like a medical diagnosis or something like that.
Exactly, and that brings us to this idea of explanatory debugging.
Okay.
Which is basically using those explanations to find and fix those flaws in your model.
Okay, I like that.
And there are two main types of local explanations that people are using for this.
Okay.
One is called input attributions.
Okay.
And the other is called example attributions.
Okay, so input attributions, are
Yeah.
those like the heat map things we've seen, or
Yeah, exactly.
that show, the model is really focusing on this part of the image or whatever?
Exactly. So if you have like a model that's deciding whether or not to approve a loan, an input attribution might show you that it's really focused on the applicant's salary and their age. So
Yeah.
you're getting insight into what the model is paying attention to.
And some techniques we've seen in the past
Yeah.
that do that are like lime,
Lime, exactly.
breadchem.
Gradcam. Yeah, those are two popular ones.
Okay, so that's input attribution. Now what about example attribution?
So example attribution is kind of cool because it's like, imagine a doctor,
Okay.
right? And they're diagnosing a patient
Hmm.
and they say, well, I've seen a case like this before.
You remind me of.
This is what happened. Yeah, exactly.
Yeah.
And so it's kind of like that. It's the model saying, hey, I've seen something similar in my training data, and this is why I'm making this prediction.
So it's using those similar cases as like a justification for its decision.
Exactly. It's like a precedent.
Oh, interesting.
Right. And this is particularly useful in fields like medicine, where you do a lot of that case-based reasoning.
That makes sense. And the paper mentions influence functions, or IFs,
Yes.
as a way to sort of quickly determine which of those training examples are
Exactly.
the most influential.
So IFs they're really efficient because you don't have to retrain the whole model to figure out
Oh, okay.
which examples are the most influential.
That makes sense.
So it's like a shortcut, and it's really helpful when you're dealing with these really big, complex models.
Okay, so we have all these great explanation tools.
Right.
But how are we actually using them
Yeah.
to debug the models in the real world?
So there are a few different approaches that the paper talks about.
Okay.
One is called XIL, which stands for Explanatory Interactive Learning.
Okay, XIL.
XIL, yeah.
Right.
And it's basically taking this idea of active learning,
Right.
where the model's asking for labels on new data, but it's also asking for feedback on its reasoning.
So it's not just, hey, was this? It's like,
Yeah.
here's why I think it's this. Am I right?
Exactly. It's like, am I on the right track?
Interesting.
And if the user spots a flaw in the model's logic,
Yeah.
they can provide that correction. So, for example, they might say, hey, you're paying too much attention to the applicant's zip code.
Yeah.
You should be looking at their credit history.
That's smart.
Right. And then you have techniques like SAPI,
Right.
which use that feedback to align the model by basically generating these synthetic examples.
So it's tricking the model into...
It's like subtly nudging the model in the right direction.
Oh, that's cool.
By showing it, hey, this is what you should be paying attention to.
Interesting. And sensor.
Yeah.
It's another one that caught my eye.
So sensor it's really interesting because it's like a quality control system
Okay.
for your data. So it's looking for those potentially mislabeled examples.
Right, which we all have, right?
Which we all have, yeah. And
Yeah.
it's asking for a second opinion.
Oh, clever.
Right. And the really clever part is it's using those IFs, those influence functions, to figure out which examples might be causing confusion.
Oh, smart.
So it's like, hey, I'm not sure about this one. Can you double check it?
Oh.
And then you can fix those errors.
So both XIL and sensor are about sort of,
They're about improving the model's knowledge.
iteratively refining the model.
Yeah, it's like this constant feedback loop, right? Where explanations are crucial for understanding and then for improving the model.
Now, we've been talking about local explanations.
Right.
Is there a way to get a more sort of global view of the model's behavior?
Yeah, so local explanations they're great for giving you that kind of zoomed in view.
Yeah.
Right? But global explanations, they give you the big picture.
Right.
And one of the most powerful ways to do that is through something called rule-based explanation.
Rule-based explanations, okay.
So it's kind of like what it sounds like. You're trying to capture the model's behavior as a set of rules, like if-then statements.
So instead of just seeing which inputs are important,
Right.
you get this set of rules that explains how the model is actually making its decision.
Exactly, and it's all in plain English, so it's much easier for humans to understand. Oh, that's great for transparency.
Exactly, and it's great for control too, right? If you understand the rules,
Yeah.
you can predict how changes are going to affect the model's behavior.
You take away the mystery.
You take away the mystery, you get rid of those black box surprises.
Right.
And what's even more exciting is that you can actually use those rule-based explanations to directly edit the model's behavior.
Okay, now we're talking. How does that work?
So imagine you have a rule that says, approve loan if salary is greater than $50,000 and credit score is above 700.
Okay.
You, as the expert, you might say, well, that credit score threshold is too high.
Yeah.
Let's lower it to 650.
Right.
And you can literally just edit that rule, and now the model's going to be less stringent.
Wow, that's so much more direct
It's so much more direct.
than just giving it, labeled examples.
Exactly. It's like you're rewriting the code.
Yeah, you're basically reprogramming it.
Exactly. And that level of control, it just has huge implications for how we think about transparency and trust in AI. Now, the paper mentions some systems that do this.
Yeah.
And one that caught my eye was FROTE, F-R-O-T-E,
Froti.
which encodes the user's feedback as synthetic data.
Yeah, so FROT it's really clever
Okay.
because it's bridging that gap between those rule-based edits that we were just talking about
Right.
and traditional machine learning.
Okay.
So instead of modifying the model directly,
Right.
you express your changes as rules, and then FROT takes those rules and it generates new data points that embody those rules.
It's like you're giving the model examples
Exactly.
that show it what you want it to do.
Yeah, illustrate your intended changes. Yeah.
But the model never sees the rules.
The model never sees the rules directly, right? It just sees the data.
That's fascinating.
So it's still learning from data,
Right.
but you're shaping that data based on your expert knowledge.
So you're still using data-driven learning, but you're controlling the data.
You're controlling the data, yeah, and it allows for those more complex adjustments while still being interpretable.
Oh, that's really cool.
And then there's another technique that's mentioned called the overlay technique,
Overlay technique.
which is kind of like a temporary fix.
Okay.
So you're basically combining a rule-based surrogate model with the original black box model.
So you're not retraining the whole system.
You're not retraining the whole system every time you make an edit.
Okay.
You're just using the rules as like a filter.
Okay.
Right? So the data comes in, it hits the overlay applies the rules, and then it passes it on to the black box model.
So it's like a quick way to test your edits.
It's like a quick way to prototype and test your edits before you fully bake them into the model.
Right.
So it's a sandbox for experimentation.
Now, all these rule-based approaches,
Yeah.
it seems like they rely on the original features that the model is using.
Right.
But what if those features aren't very meaningful?
That's a great point.
Or interpretable to begin with?
And that leads us to this even more cutting-edge area of research,
Right.
which is concept-based models and neurosymbolic AI.
Concept-based models. So this is like, are we trying to teach machines to think in concepts?
We're trying to teach machines to think like humans.
Okay.
Right? To use abstract concepts.
Right. Not just like, this pixel is bright.
Exactly. So traditional explanations, even with those rule-based approaches,
Yeah.
they can be limited because they're tied to those individual data points.
Okay.
Right? So imagine trying to explain why a model thinks a certain image is a cat.
Right.
If it's just highlighting pixels, it's really hard to know if it's recognizing the shape, the fur, the eyes.
It's the difference between recognizing words and understanding the sentence.
Exactly.
Right.
And so concept-based models, they're trying to bridge that gap
Okay.
by incorporating those higher-level concepts into the decision-making.
So instead of just seeing pixels, it sees cat, fluffy, sitting indoors.
Exactly.
Okay.
Learning to recognize and use those abstract concepts, just like a human would.
And that opens up a whole new world of possibilities for interacting with it.
Oh, absolutely. Because now, instead of tweaking those individual pixels
Right.
or features.
You can give feedback on the concepts themselves.
Exactly.
So you can be like, no, fluffy is wrong.
Right.
That's for dogs, not cats.
Pay attention to the ears.
Right. Ears are more important.
Exactly. And because those concepts are more abstract, that feedback you're giving, it generalizes to more situations.
It's more efficient.
It's way more efficient. Yeah.
Okay. So how are these concept-based models actually built?
So that's one of the big challenges in this field, and there are a bunch of different approaches.
Okay.
Some models learn those concepts in an unsupervised way. They're just looking for patterns in the data.
Right, just finding clusters.
Finding clusters, yeah. Others use prototype representations, so they're associating concepts with specific examples.
So like cat would be represented by a bunch of cat pictures.
Exactly, and then there are other approaches where you're actually getting those concepts from human experts.
Oh, interesting.
Right, so you're making sure that they're aligned with our understanding.
So you might ask an expert to, like, define cat.
Define cat. Give examples of cats.
Okay.
Yeah, and that leads us to this really fascinating area of neurosymbolic AI.
Neurosymbolic AI.
Which is all about trying to combine deep learning with symbolic reasoning.
Okay.
So you're bringing together the power of pattern recognition
Right.
with the ability to manipulate those abstract symbols and logic.
That sounds like we're on the verge of, like, real AI.
It's definitely a frontier, yeah.
Yeah.
But we're seeing some really cool approaches that are using neurosymbolic explanations for that interaction.
Oh, cool.
So, for example, some systems let you give feedback as logical statements.
Oh.
Right. So instead of saying, this image should be a cat, you could say, if it has pointy ears, whiskers, and a tail, it's probably a cat.
Right.
So you're not just labeling.
You're teaching it rules.
You're teaching it rules. Yeah, you're teaching it to reason.
That's amazing.
And that kind of high-level feedback, it can be really valuable for making those systems more robust and more trustworthy.
Now, all of this is super exciting, but I'm sure there's still some big challenges
Oh, absolutely.
in this area.
One of the biggest challenges is making sure that those concepts that the model is using are actually meaningful to humans.
Right.
We don't want to just replace one black box with another.
Right. We don't want to be fooling ourselves thinking it understands.
Exactly. We need to be careful that we're not just, making up stories.
Right.
And then there's also the challenge of, how do you design the interfaces and the interactions so that they're intuitive for people to use.
Yeah, usability is huge.
Usability is huge, especially if we want non-experts to be able to work with these systems.
Exactly. It feels like we're really at this point where,
it's a new era.
AI is becoming more than just a tool.
It's more than a tool. It's becoming a partner.
It's a collaborator.
It's a collaborator.
In knowledge discovery.
Absolutely. And it's the shift from just training models to actually working with them.
Right.
That's what's so exciting.
And a big part of that is
Explanations.
these explanations.
Explanations are key.
Okay, well, this is a great place to pause for now, I think.
Yeah, sounds good.
We've covered a lot of ground already.
A lot of ground.
And we'll be back in the next segment to dig even deeper into some of these concepts.
Looking forward to it. So we were talking about these rule-based explanations, really interesting stuff. Let's dive a bit deeper into how they actually work, the nuts and bolts.
Yeah, because it sounds great in theory, but how do you actually get these rules out of the model?
Right. So there are a bunch of different algorithms out there that can do this. Each one has its own strengths and weaknesses. Kind of depends on what you're looking for.
Okay, so the paper mentions low-error, BRCG, and GlocalX.
Yeah, those are some of the popular ones.
What are the main differences between them?
Okay, so Lore, that one focuses on making rules that are really accurate, but just around a specific instance, kind of like a local explanation.
Okay, so very specific.
Very specific, whereas BRCG, that's more about getting rules that apply globally, like capturing the big picture of how the model works.
Oh, interesting.
And then you've got GlocalX, which tries to do a bit of both, rules that are accurate locally but also make sense globally.
Find a good balance.
Yeah, find that sweet spot.
So it's pretty amazing, right? You're taking this complex model and distilling it down to a set of rules that a human can actually understand.
It's pretty cool, yeah.
But I mean, if you end up with like a million rules, that's not really helpful, is it?
You're absolutely right. You need to keep it concise, find that balance between staying true to the original model, but also making the rule set simple enough that a human can actually work with it.
Right. So it's got to be accurate, but also manageable.
Exactly. Yeah. And this is where things get really interesting with rule-based explanations, because they're not just for understanding.
Right.
We can use them to actually change how the model behaves.
That's what's so cool about this. It's not just passive. You're in control.
Exactly. You're not just observing, you're shaping the model.
Right, like an AI sculptor.
I like that, yeah. So picture this. You've got a rule that says, approve the loan if the salary is over $50,000 and the credit score is over 700.
Okay, pretty standard loan stuff.
Yeah, but you, the expert, you might look at that and say, hold on, that credit score limit is way too high. Let's drop it to 650.
Okay, so you just change the rule.
You just edit the rule and boom, the model is instantly less strict.
Wow, that seems so much more efficient than like trying to retrain the model with a bunch of new examples.
It is. It's so much more direct and intuitive, too. You're basically working with the model's logic directly.
Yeah, you're getting under the hood.
Exactly. And that makes such a big difference in terms of transparency and trust. You can actually predict how those changes to the rules will affect the model's decisions.
No more black box mystery.
Exactly. Now, remember RFRT, that system we talked about earlier?
Yeah, the one that uses synthetic data.
Right. Well, that's a really smart way to bridge this gap between editing the rules and, the traditional way of training a model.
Okay, so remind me how that works again.
So instead of changing the model directly, you basically tell FRT what you want to change, like make the credit score threshold lower.
Right.
And FRT takes that and generates new data points that reflect that change, like examples where people with lower credit scores get approved.
So it's like giving the model hints without actually showing it the rules directly.
Exactly. You're guiding its learning without messing with its internal workings.
Pretty sneaky.
It's pretty clever, right? And the model is still learning from data, which is what it's good at.
So you get the best of both worlds.
Exactly. The flexibility of data-driven learning, but with the control and transparency of rule-based editing.
Really powerful stuff. Now, what about that overlay technique? That's sounded kind of like a quick fix.
Yeah, the overlay is a cool way to implement changes fast without retraining the whole model, which can take a long time.
And the paper said it uses a rule-based surrogate model on top of the original black box model. How does that actually work?
Think of it like this. The overlay acts as a filter, sitting on top of the black box. New data comes in, it hits the overlay first. The overlay checks the rules you've set, and then passes the data to the black box model to make the prediction.
Oh, so it's like a temporary patch, almost.
Yeah, that's a good way to think about it. You can test out different rules quickly, see what works, before you bake those changes into the main model.
Like a sandbox for experimenting.
Exactly. But all these rule-based methods, they still depend on those original features the model uses.
Right, the same ones we were talking about earlier.
And you brought up a really important point. What if those features aren't very meaningful or easy to interpret to begin with?
Yeah, like what if the features themselves are kind of a black box?
That's a really sharp observation, and it leads us to some of the most cutting-edge research happening right now. Concept-based models and neurosymbolic AI.
Concept-based models. That sounds familiar. Weren't we talking about those earlier?
We were, and they're so important, they're worth a deeper look. They offer a way to go beyond those limitations of feature-based approaches.
Okay, so we're trying to teach machines to think more like humans, using concepts instead of just data points.
Exactly, because even with rule-based explanations, you're still tied to those individual features, and that can limit how much you can really understand what's going on.
Right, like if the model is looking at a picture and just focusing on the pixels, we might not know if it's recognizing the shape, the color, the texture.
Exactly, and that's where concept-based models come in. They try to bridge that gap by using higher-level concepts as part of their decision-making process.
So instead of just seeing pixels, it's understanding cat, fluffy, sitting.
Precisely. It's learning to grasp the meaning behind the data, not just the data itself.
And that has to open up a whole new world of possibilities for how we interact with these models.
Absolutely. Now, instead of fiddling with those individual features, you can give feedback on the concepts themselves.
So you can say, hey, model, you're putting too much weight on fluffy when you're trying to identify a cat. Focus more on the shape of the ears.
Exactly. And because concepts are more abstract, that feedback is way more powerful. It can apply to a wider range of situations, so the model learns much faster.
More bang for your feedback buck.
Exactly. But now the question becomes, how do you actually build these concept-based models? Where do these concepts come from?
Yeah, that's a good question. It's not like you can just download a dictionary of concepts for the model to use.
Right. It's tricky, and there are a bunch of approaches being explored right now. Some models learn these concepts all on their own, just by finding patterns in the data.
Sort of like unsupervised learning.
Exactly. They're looking for clusters and relationships in the data without being explicitly told what to look for. Other models use something called prototype representations, where they link concepts to specific examples.
Oh, so like cat would be linked to a bunch of pictures of different cats.
Precisely. And then there are some approaches where you actually involve human experts to define those concepts.
Oh, that's interesting. So you might have a team of biologists defining cat for a model that's analyzing animal images.
Exactly. It's all about making sure the model's understanding aligns with our human understanding.
It's like we're building a bridge between human knowledge and machine learning.
I love that analogy. And that bridge leads us to the fascinating world of neurosymbolic AI, which tries to blend deep learning with good old-fashioned symbolic reasoning.
So we're combining the power of pattern recognition with the ability to work with abstract symbols and logic.
Exactly. We're trying to create AI that's more holistic, more like how humans think. And we're already seeing some really cool applications of this, particularly when it comes to explanations.
Okay, tell me more about that.
Well, for example, some systems now allow users to give feedback in the form of logical statements, almost like writing little programs.
So instead of just labeling data, you could say something like, if an animal has pointy ears, whiskers, and a tail, it's probably a cat.
Exactly. You're not just feeding it data, you're teaching it how to reason, how to make inferences.
That's amazing. It's like we're taking machine learning to a whole new level.
We are, but of course, there are still challenges to overcome. One of the biggest is making sure those concepts the model uses are actually meaningful to us humans.
Right. We don't want to just swap one black box for another more complicated one.
Exactly. We need to be careful that we're not just tricking ourselves into thinking the model understands when it's really just learned some weird correlations in the data.
So we need ways to check the model's understanding and make sure it aligns with our own.
Exactly, and that's not always easy. Plus, we also have to think about the user interface, How do we make all this accessible to people who aren't AI experts?
Right. If the explanations are too technical, nobody's going to use them.
Exactly. So we need to find that sweet spot. Powerful techniques that are also easy to understand and use.
Powerful AI that's actually useful for people in the real world.
That's the goal. And
Yeah.
as this field keeps developing, we can't forget about the ethical implications.
Oh, right. Like, how do we make sure these systems are used responsibly?
Exactly. How do we prevent them from being misused or biased? These are big questions we need to grapple with as we create more and more powerful AI.
It's a lot to think about, but it's exciting stuff. It feels like we're really on the cusp of a new era in AI, one where these systems are more than just tools, they're partners.
I agree. It's about humans and machines working together, not just machines doing our bidding. And explanations are key to making that partnership work.
That's a great point. We've covered so much ground already. I think it's a good time to take a break and let everything sink in.
Sounds good to me. So we've been digging into these concept-based models. They really seem to be a game changer for making AI more transparent, more interactive.
Yeah, and we were talking about how one of the biggest advantages is that you can give feedback at the level of concepts.
Right, not just fiddling with individual data points or features. You're talking to the model in a language that's closer to how we humans think.
It's like you're teaching it the underlying principles, the why behind the data.
Exactly, and that shift in how we think about AI, that's what's really exciting.
Yeah, it changes the whole game.
Yeah.
So for example, let's say you're using one of these concept-based models for a medical diagnosis.
Okay, yeah.
Instead of just getting a prediction like high risk of heart disease, you might get an explanation that breaks it down by concepts. Like, okay, you've got elevated blood pressure, there's family history of heart disease, and your EKG results are abnormal.
Right, so you're not just getting a yes or no answer, you're getting insight into the model's reasoning.
Exactly. And that lets you have a much more meaningful conversation with the model.
Right. Absolutely. You can ask questions like, okay, how important is each of these factors? Or are there any other concepts that might be relevant here?
It's almost like talking to a doctor who can explain their thinking in a way you can understand.
That's the goal. And as these concept-based models get more sophisticated, imagine the possibilities for collaborating with AI on things like scientific discovery, personalized medicine.
Yeah, the potential is huge. But even with these concept-based models, I imagine there are still some challenges.
Of course, no technology is perfect. One of the big ones is making sure those concepts the model uses actually align with how we humans understand them.
Right, we don't want to create a system where the model is using concepts that are meaningless or even misleading to us.
Exactly. It's like we're trying to have a conversation, but we're speaking different languages.
Yeah, that wouldn't be very productive.
Yeah.
So we need to find ways to check the model's understanding and make sure it's on the same page as us.
Right. And we also have to be careful about bias. Just because a model uses concepts doesn't mean it's immune to biases that might be present in the data it learned from.
Oh, that's a good point. So we still need to be vigilant about those kinds of things.
Absolutely. We always have to be thinking about transparency, accountability, making sure we can understand how these models work and why they're making the decisions they're making.
And that's where this idea of interactive machine learning really comes into play, right? Giving users the ability to give feedback and help steer the model in the right direction.
Exactly. It's about collaboration, not just blind trust. So as we wrap up our deep dive into interactive machine learning, what are the big takeaways?
Well, I think the biggest one is that explainable interactive AI is not just some fancy add-on. It's crucial if we want to build truly trustworthy AI systems.
I agree. It's about moving beyond the black box and creating AI that people can understand, work with, and ultimately trust.
And concept-based models, along with all the other advances we talked about, those are the building blocks for that future.
It's an exciting time to be working in this field. We're really pushing the boundaries of what's possible with AI.
Absolutely. So to all our listeners out there, keep learning, keep asking questions, and keep pushing the boundaries of what's possible with AI. That's all for this episode. Thanks for joining us.